Thanks for that kind introduction. So over the last years, I've been working on industrial automation in the field of architecture. A number of years ago, in 2012, I set up a startup company in the field of industrial robotics, specially tailored to the construction industry, called PythonOCC Formwork Robotics. I've been working as an architect for a long time. So I've been co-founder of the architecture practice based in Paris, ECD Architecture and Design Research. Currently, I'm wrapping up my PhD research, which is also somewhat tangential to the things I'm presenting here today. And I've been a long-term PythonOCC developer. So just to give you an outline of the talk, I'm going to hopefully convey to you why PythonOCC is relevant. In order to do that adequately, I need to speak about the CAD industry and open source software. So a little bit of context is, I think, required to fully appreciate things. I'll address why PythonOCC is an enabling technology, and specifically how it enabled my startup company, PythonOCC Formwork Robotics. We'll speak about some of the mathematical underpinnings of computer-aided design and differential geometry. As a developer, I guess the first thing to look is, what kind of data types are we handling? So I'll try to introduce you the concept of CAD a little bit in the form of data types. And whom of you is a fan of Conda? So the next two of us. Well, Conda is pretty easy. So imagine that these CAD libraries are vast, being comprised of many hundred of megabytes of libraries, and quite challenging to compile. So, it always used to be quite difficult to distribute these kind of Python modules with complex dependencies, and Conda really resolves that adequately. So in the beginning of our project, it really took, it could take somebody maybe a day to, compile the stuff for its platform. It's like, compiling a Titanic or something, right? It's not for the faint-hearted. So nowadays we can sort of install this software in 5 minutes or so. So when we speak about CAD kernels, is that it's a kind of core enabling technology for a multitude of domains. So CAD kernels are central for computer-aided design, which is just, Autodesk, AutoCAD, CATIA, Rhino, all these kind of cool design softwares. Computer-aided engineering, where you're sort of solving partial differential equations through finite element analysis. And these analysis meshes are derived from the CAD geometry, where CAM is kind of deriving manufacturing data, toolpaths, the kind of slicing of your geometry for 3D printing. That is computer-aided manufacturing, which is also deriving all of this data from CAD kernels. Now, why I think PythonOCC is an interesting project is that open source has taken our world by storm, right? And the leading platforms, when you think of Linux and Android, when you think of PostgreSQL, there's almost no technology where open source either has a place or is maybe even dominant, right? The dominant technology. So the thing is that CAD is a really different domain. So in the CAD industry, it's like people still party like it's 1999, right? So it's been relatively untouched by the influence of open source software. There's one exception, which is the Open Cascade project. So in the 80s and 90s, there was a company leading CAD innovation in Europe, which is called Matra Data Vision. And in the mid-90s, they started to develop their second system, right? So their early system was built in Fortran. They started to develop a next generation system in C++. And basically the company tanked due to second system syndrome, right? So the software was sort of being sold or to customers while being fully developed. And as a consequence of that, the company tanked. Then some components were sold off to companies like Dassault, which were integrated in CATIA. CATIA is the leading platform in CAD. So you have to realize that this is a kind of a cathedral of software development, right? Many hundreds of man-years have been invested into it. And I guess that some basic statistics to substantiate it is that the software is comprised of 9,000 classes. Just the include files is 15,000 include files, right? So it's a behemoth of a software package. The development started in 1996. Currently, there are 130 developers maintaining that CAD kernel and further developing it. But my point is that there is no alternative for this CAD kernel. Like, if open source CAD is going to be a thing, this is the enabling technology. That effort won't be duplicated because industry, and it's really, my opinion goes really against it. Industry considers CAD too much of a solved problem, which is also substantiated in softwares like CATIA, right? Imagine that a design team designs an airplane like the Boeing 777, simulates it, builds it, and then it actually flies, right? It's like, it's an incredible achievement in software development. So I met Thomas Paviot, who initiated the PythonOCC project, because we were tinkering in the backyard of these software packages of CATIA, right? And for instance, Thomas implemented a kind of dynamics engine. You know Angry Birds, right? That's a dynamics engine, right? When things are crashing and colliding, those are dynamics. So he implemented a kind of 3D dynamics engine as sort of an informal plugin into CATIA, and Thomas was let known that these kind of efforts weren't appreciated, right? Because if you want to develop a plugin, you have to, it's challenging first of all, but you have to buy an SDK, right? You have to license yourself as a developer to do serious stuff. So as a user, as a user, you can do some basic automation in VB, but that's about it, right? So we had a real need we really needed a kind of different platform for our experiments. So when Thomas started to wrap OCC in Python, I guess these kind of screenshots convey the sentiment that I felt, right? Because CAD is such a restricted environment for development, I think, that, you know, Mel Gibson does a great job of expressing that feeling. But also the thing is that, imagine that I really do think it's like almost an archaeology, right? That you find this incredible cathedral and almost, it gives way to new ways of creating CAD softwares. So before you had to shell out big time, in a sense, for expensive NDKs or live with Visual Basic, which neither nor is an option, I think. So another way of saying is this, right? Can you stomach compiling hardcore C++ code of such a vast library, or can you stomach with Visual Basic VBA, which is even worse than VB? So also just From the perspective of just the programming languages, I thought neither was a very satisfactory option. So Python is there in the center, in a sense, right? So it allows you to go as deep as you would be able to with C++ APIs, though the development speed is incredibly fast and a lot more fun. So kind of my mental image of our project is like a hot rod, right? Is that you have this fantastic, phenomenal, huge, somewhat aging project, and you insert a new, fresh engine into it, and that thing becomes completely irrelevant again. So a Python wrapper is not just neutrally providing access to that library, it becomes something different in itself entirely. So perhaps a way to phrase that is that, the C++ API is something for software engineers by software engineers, while the Python API is built by engineers for engineers. So it's quite a transition. The PythonOCC team, the project, as I said, the project was initiated by Thomas Paviot. At the time, I was living in Paris. So it was a great project to initiate there. Recently, we've been getting quite a few cool contributions from a developer of the German aerospace agency, Martin Sigel. So now I'll try to present to you what kind of development this software enables. So normally a CAD software is a graphic user interface application, right? Which is quite limiting in the sense that the kind of designs I was making at the time were very much performance and simulation driven. So, for instance, this gallery is optimized such that throughout the whole day, throughout the whole year, the gallery is lit by 300 lux of sunlight. So it's an easy problem to define, but you can't ask an architect, like, draw me a window of 200 lux. That's an absurd question, right? Though through evolutionary computing, you can completely solve this. So evolutionary computing is like an amplifier for your design thinking, and it kind of allows you to pierce through your ceiling of rationality. And by that I mean you can arrive at designs that are very rational, but lie beyond what you're able to rationally achieve by your own traditional means. So that means that you're generating tons and tons of design variations, and just graphic user interface software is not built for that. Right? So if you have a CAD kernel, you can generate endless kind of forms, evaluate at infinite element engines, or in this case, Radiance, an engine for photometric validation. So that was sort of a need from my design perspective. So at the time, I was getting more and more interested in being able also to manufacture and fabricate from the designs that I was producing. So these are some of the early attempts of doing design generation through PythonOCC, where there are some quite sophisticated geometric conditions that I wanted to achieve. So for instance, for this table, there where the rings are touching, there's a geometric continuity. So that means that the tangents are in the second, are curvature continuous, right? Which generates this. So if you trace the rings with your finger, this kind of beautiful continuity amongst the elements of the geometry. So continuity is kind of also a criteria of how good your CAD software is. And a great example is, for instance, the Maiming project, which is currently built in Taiwan by Meccano Architecten, a Dutch architecture office based in Delft. And a friend of mine, Sander de Boer, has been brought on the team as a geometry consultant, who has been pivotal in kind of realizing these kind of projects. And continuity is very difficult to achieve. The kind of continuity he was looking for is second-order continuity. So think of the panels that make up the bodywork of your car. Now, you'll see that the reflections of the car are continuous. And in order to, the geometric requirement to have these kind of continuous reflections is that the panels are not just meeting at a point, or not only tangentially connected, but curvature connected. So second order continuity. And only very high-end CAD kernels can achieve this kind of continuity. So you see that the orange surface is curvature continuous with the green splines generating the surface. So actually, also in these kind of CAD, there's few ways of modeling this in a nice, kind of cool way. So Sander was really putting PythonOCC to the test and was asking us, can we generate these Class A surfaces, as they're known, in PythonOCC? And it was kind of a miracle for us to see that, that we can actually achieve that. So you see these these four surfaces, and you see that the curvature continuity is perfect. There's a smooth transition from one surface patch to the other. So here you see sort of the control points of the Bezier surface that are solved in order to meet this condition. And this is rather advanced. So PythonOCC is very good for, you import simple geometry and you generate a lot of sophisticated geometry from your basic input geometry. That's a process I've been working on quite a bit. So these are kind of designs that are really challenging for traditional CAD systems to produce. And I think PythonOCC has a place there. So CAD is really about higher order geometry, right? So meshes have finite precisions, and for fabrication analysis, you need to compute exact first and second, even third order derivatives from the surface. You can't do that with a mesh. So the kind of data we're using are boundary representations. So think of a point in space and a normal, right? So now you have that end it's called the half space, right? So you've divided space into A and B, right? It's either on that end of the normal or on the opposite side. So these surfaces are connected through edges. Edges are connected to vertices. And those make up the CAD topology. In order to be able to visualize CAD surfaces, you need to discretize them, right? So you're always observing meshes rather than the actual NURB surfaces. So to give you a quick intro into what is the mathematical definition of NURB surfaces, this is a basic NURB spline. Now you see that those brown points, those 4 brown points are the input, the control points. You see that the orange points lie are, let's say, at about a third of the distance between the points, right? You see that the pink point on the Bezier spline is also at about a third of its length, right? So you see that this is what's called a third order Bezier curve, because in a sense, the spline the line that is made up with the 2 white control points is the third level, let's say, of linear interpolation. And that generates a Bezier curve. So you need to evaluate this equation for every point on the Bezier spline in order to be able to evaluate it. So these surfaces, you can generalize this to 2D surfaces as well. And also elements can be cut out of the surface. So These domains are nonlinear, but can also be discontinuous. So that can be quite challenging to evaluate. Also, when they are meeting at an edge is not just a line, right? You have to consider it more of a cylinder, because you also have to deal with round-off errors. So CAD is quite challenging. So all of these surfaces are basically 2D rubber patches in a sense, right? So on top you see a 2D space embedded in 3D space, while on the bottom of the image you see the 2D UV domain with the cookie cutting, in a sense, the trim applied. So PythonOCC also enables computer-aided engineering. That means that we can discretize these CAD elements. For instance, here you see the discretization of kind of a wing. That means you can generate many variants of your design and evaluate, for instance, how it's performing in terms of lift or aerodynamics. And these kind of design loops, these design optimization loops, are traditionally quite challenging to produce in CAD software. So, for instance, the German aerospace industry is also building frameworks on top of Open Cascade to evolve conceptual airspace designs. A recent field we've been tapping into with PythonOCC is the construction industry, which is really based on building information models. And in order to reconstruct the geometry from a file type, you need a very performant CAD kernel. So a friend of mine, Thomas Keijnen from Technical University of Eindhoven, has built such a parser that reconstructs the building model in 3D. So this really opens up, it's a kind of foundational technology. Now that you can do this, you can evaluate, you can derive lots of interesting things from it. For instance, 2D plans, or evaluate its performance, generate manufacturing data from it. And he did it at such a great level that also the next generation of this format, which supports curved shapes, is also already supported, while actually more standard industry applications are somewhat lagging behind. So a field I'm personally very interested in is computer-aided manufacturing. So here we see, for instance, a tooling path that a milling tooling path derived from this surface being computed in PythonOCC. The software I'm currently working on, PyRapid, does this for industrial robotics. So it facilitates the transliteration from geometry to robot motion. So translating is from one language to another language, right? So transliteration is when you have to translate something, but across domains, right? So the domain that we're crossing is we're transitioning here from geometry to robot motion, which are very different domains in a sense, right? So this software is kind of like a compiler, a form compiler for a robot. You load in your CAD data and you try to automatically generate the tooling path. You try to derive motion from your geometry. And the thing is that we apply this technique to produce very large molds for the building industry. This is one of the first projects I created to explore these kind of fabrication techniques. So this is a pavilion of 9 meters by 9 meters in length, 4.5 meters high. And the thing is that increasingly I think of architecture as the discrepancy between the cost of material and labor versus the market value. Do you see what I mean? And robots are very important to maximize this discrepancy. So for instance, this pavilion, in terms of material, was rather inexpensive, while there's no alternative way to really produce it, it would cost 50, 60,000 euros to produce it. And I was able to do it for very little means at some point. So there have been few methods that are really well suited to very large-scale fabrication. Like something that few people realize is that 3D printing does not that naturally scale to architectural proportions, right? So there's 1 million cubic centimeter in a cubic meter, right? So if your technique is relevant on the cubic centimeter, you have to go up 6 orders of magnitude before it becomes relevant to the construction industry, and that's not easily achieved. So something that we do is we cut a lot of formwork out of cheap styrofoam. You see these kind of robots mounted on linear tracks, so you can imagine the kind of volume that they can process in little time. So at the moment we are constructing the new Lego headquarters, or the company owning Lego in Denmark. So we're producing about 5,000 square meters of formwork. That's about 130 truckloads of formwork to create the molds for this really sophisticated, very challenging building. So the thing is that once you've constructed the mold, well, casting the concrete from the molds is a challenge, but let's say 60, 70, sometimes even 80% of the cost involved is in actually creating the molds. So it's quite an enabling technology to really be able to construct more elaborate design at a very large scale. So by this project, we really have the feeling that we've kind of proven this concept on an industrial scale. Something that I've done recently, purely for kicks, is I've applied this kind of technique of wire cutting with a diamond wire, right? So you have this extremely powerful diamond wire cutting through marble pieces. And actually that technology is now also being utilized in serious kind of production work. So, creating your own tools is really enabling to, for me, technology is a way that I can exercise my profession in an acceptable way. You have to realize that architects are building 1 out of 10, maybe 1 out of 20 of their designs. So you have little to say in whether a design is going to be produced or not, right? So the generation of architects before me, my feeling is that a lot of the objective aspects of design, the engineering, were sourced out to very capable engineering offices, but actually you want your designs to be also somewhat easily manufactured. So an architect that I really look up to is Jean Prouvé, who was an architect who had his own factory, and hey, my pointer stopped working. Could you, if I do this, can you transition to the next slide? Yes, please. Okay. Pardon? Okay. All right. Well, I think I'm adequately interrupted by my presentation, pretty much being halted. So I'm being alarmed through technology. But Prouvé was able to, produce these kind of houses at his own factory, and that's kind of my long-term ambition, right? That you don't spend your time waiting for the ideal client, but in this, that you stop working in this kind of demand-driven way and start to transition in a kind of supply-driven architecture, right? Where you produce things from your technical capability, and through this technical capacity, you have a bit more autonomy of creating your own work. So this really goes back to modernism in architecture, in a sense, where advances in technologies are Also downstream to the common man in a sense, right? So architects tend to focus on building musea, city halls, but not houses. And I think robots are an excellent way to do so. All right.
Okay, thank you.
Thanks.